Welcome back, everyone. Ready for another deep dive? Today, we're stepping into a world, well, maybe not a world, more like the code of the universe, really. We're talking number theory.
And not just any number theory. We're diving headfirst into a paper that tackles two of the big ones, the Dirichlet Divisor Problem and the Gauss Circle Problem.
Yeah, these aren't your average back-of-the-napkin math problems. These are, they're notorious for, well, for stumping mathematicians for, like, centuries.
Centuries is right. In this paper, it takes a truly unique approach, trying to crack the code with a little help from probability.
Probability. Okay, hold on. We're talking about precise numbers here, right? Like solid, unchanging numbers. What does chance and probability have to do with any of this?
That's the beauty of this, well, of this whole paper, really. It connects those seemingly totally different worlds. You know, it's like saying the way trees sway in the wind can actually help us understand how sound travels.
Okay, I'm intrigued, but I think we got to back up a bit for our listeners. Before we get to the probability part, let's break down these two problems, starting with the Dirichlet Divisor Problem. What's the deal with that one?
Right. So imagine you're, I don't know, slicing up a cake for a party. The divisor problem, it basically looks at how many different ways you can cut that cake into equal pieces as your party gets bigger and bigger.
Okay, so far so good. Like a small party, easy peasy, but a huge party. Things could get messy.
Exactly. And I don't just mean messy frosting. The math gets seriously complex.
Right.
We're talking about diving into these wild formulas and uncovering, well, really unexpected patterns in how numbers behave.
So like division on steroids? Okay, I think I'm getting it. Now what about this Gauss Circle Problem? What's that all about?
All right, picture a dartboard. It's a classic pub game, right? The circle problem asks, as that dartboard changes size, how does the number of darts landing inside those circles change? Sounds deceptively simple, yeah.
Right, like bigger dartboard, more darts at the circles, proportionally.
You'd think so, wouldn't you?
Yeah.
But like I said, things get complicated. The deeper you go, the more intricate the connections become. And that's where this whole probability thing comes in.
Okay, yeah, you keep teasing that. So how does probability, like chance and randomness, how does that fit into these really precise, really old mathematical puzzles?
Well, at the heart of both of these problems are these things called error terms. Basically, we have formulas, right, to try and predict the answers. But there's always this tiny little gap between what the formula says and the actual answer. That gap, that's our error term.
So like the formulas are almost right, but they always miss the mark by just a little bit.
And it's that little bit that's so fascinating. These error terms, they're not just random mistakes. They actually behave in really specific ways that have been driving mathematicians crazy for, well, you guessed it, centuries.
It's like these error terms are hiding secret messages within the numbers. So is that where probability comes in? To try and decode those messages.
You're catching on. That's precisely what this paper does. It uses something called random trigonometric series. And now, I know that sounds intimidating.
Yeah, a little bit.
But just think of it like this. It's a way to model the randomness, the unpredictable dance of those error terms, you know, like trying to predict the path of a leaf floating down a river. It's chaotic, but there might be hidden currents, underlying patterns that we just haven't uncovered yet.
So, okay, we're trying to find those hidden currents, those patterns in the chaos. Did this whole probability approach work? Did they find those patterns in these error terms?
Well, that's the really interesting part. This paper, it compared the way these error terms are distributed to what you'd expect from a purely random model, like if you were flipping a coin, right?
Yeah, get this. The error terms, they lined up with the coin flips. There was a pattern.
There's definitely a connection, yeah. A surprisingly strong one. It suggests that those error terms, as random as they seem, they actually follow a deeper structure. But of course, there's always a but in math, right? This is where we bump into a fascinating concept, something called linear independence of square roots.
Okay, you lost me. Linear what now? That sounds a little beyond my pay grade.
Yeah, and it's pretty technical to dive into here, but basically, just think of it like this. It's like we hit a fence in our investigation. We can see there's more to discover about these error terms, but this linear independence thing kind of limits how much we can prove using this probability approach right now.
So we can see the hidden valley, we just can't quite find the trailhead to get there yet.
Exactly. A perfect analogy.
Yeah.
But even though we're a little stuck, the paper does offer some really intriguing clues. It starts digging into the extreme values of these error terms.
Extreme values, meaning like the biggest outliers when those error terms go really haywire.
Exactly. Most of the time, those errors are small, right?
Yeah.
But every so often, bam, you get this huge jump, this major deviation from what you'd expect. Figuring out how often those big jumps happen, how big they can actually get, well, that's a huge area of research.
So, like, we're trying to predict earthquakes now. We know they happen, just a matter of when and how bad, right?
You're getting it. And what's cool is that this paper actually builds on the work of a mathematician named Lamzouri, who made some serious headway in understanding the divisor problem specifically.
Lamzouri, didn't he use a totally different approach, though? Not probability.
You're good with the names. You're right. He had a totally different method, a really elegant one, actually, to figure out what we call an omega result for the divisor problem. Basically, he found the absolute smallest those error terms can get, the lower bound, if you will.
So he drew a line in the sand, like, error terms, you can jump around all you want, but you can't go below this point.
And what's really wild is that on top of that, Lamzouri, he made a prediction, a conjecture, actually, that this line in the sand, this omega result, it's actually really close to the true maximum size of the error term.
So it's not just a lower bound, it's practically the upper bound, too.
And here's the kicker. Even though this paper we're looking at, it takes this totally different route, right? With the probability stuff, its findings, they actually back up Lamzouri's conjecture. It's like two paths converging on the same truth.
Okay, now that's just cool. Different approaches, same answer. It seems like a win for everyone trying to understand these unruly error terms.
It's like that aha moment you get when two puzzle pieces just click perfectly into place. And it's not just the divisor problem, by the way. This paper found the same thing happens with the Gauss Circle Problem, our dartboard puzzle. Lamzouri's conjecture holds true there, too.
So 2 for 2. That's a good sign. But it does make you wonder, I mean, if this probability thing is so powerful, could it be applied to other number theory problems out there?
That is a fantastic question. And yeah, the paper touches on that. It even hints at another really fascinating area of research with something called the Riemann Zeta Function.
Riemann Zeta Function. Okay, now that one rings a bell, vaguely. But it's definitely next level math, right? I think we might need a quick refresher for those of us who might not have that one memorized.
You're not wrong. It's a big one.
Yeah.
But it's beautiful, really. Think of the Riemann Zeta Function like a map. A map that can unlock the secrets of prime numbers.
Prime numbers, right. Those numbers that are only divisible by themselves and 1. Okay, got it. They're like the atoms of the number world. So this zeta function helps us understand how prime numbers are distributed, how they work.
It's like having a key to their secret language. Now, I don't want to get too lost in the weeds here, but basically, one of the big challenges with the Riemann Zeta Function is figuring out how its values change when you plug in these things called complex numbers.
Complex numbers. Okay, now we're talking square roots of -1. Things just get a whole lot more abstract.
A bit abstract, sure, but that's where some of the most exciting math lives. So without going full-on mathematician on you here, there's this problem related to finding the second moment of the Riemann Zeta Function. It's like taking its pulse, you know? Trying to understand its overall behavior.
Checking for a steady heartbeat or if it's more of a wild drummer kind of thing.
And guess what? Just like those other problems we were talking about, the calculation for this second moment, it also has an error term. That little difference between what we expect and the reality of the situation.
Okay, let me guess. This paper finds that good old probability theory, it can help us understand this error term too.
You're on a roll.
Yeah.
It's honestly pretty mind-blowing. The paper, it suggests that this same approach, this way of looking at things through the lens of probability, it could be the key to unlocking even more secrets about the Riemann Zeta Function itself.
Wow, so we've gone from like dividing cake and throwing darts to like deciphering the fundamental code of the universe with prime numbers and zeta functions, and it all comes back to probability.
It just goes to show you, math, it's all connected. And what's even more exciting is that this is really just the tip of the iceberg. The paper hints that these results, these connections, they could apply to a whole bunch of other number theory problems too.
So this paper, it's not just an answer, it's like a whole bunch of new questions, a launch pad for a whole new wave of research.
And who knows what incredible connections and breakthroughs are waiting to be discovered. Maybe someday, someone listening to this will be the one to make those breakthroughs.
I love that. Well, this has been quite a journey. I feel like my brain just got a serious workout, but in a good way.
That's what we like to hear.
So before we sign off, any parting thoughts for our listeners, anything they should keep in mind as they continue their own deep dives into the world of number theory?
You know, I think the biggest takeaway here is that what we often think of as errors, those little discrepancies, those things that don't quite fit, they might not be mistakes. They might actually be glimpses into a deeper order, a hidden pattern that we just haven't been able to see before now.
It's like our brains are wired to see the illusion, but there's a whole other picture hidden in plain sight, just waiting for us to shift our perspective.
Exactly. And this paper, it's like it's giving us a new set of lenses, a new way of looking at those hidden patterns and unlocking a deeper level of understanding about the universe of numbers.
Beautifully said. And on that note, we'll wrap up another deep dive. A huge thank you to you, the listeners, for joining us on this exhilarating adventure through the world of number theory. And remember, curiosity is key. Never be afraid to ask those what-if questions, because you never know what hidden wonders you might uncover. Until next time. All right, get ready to dive deep, because today we're tackling number theory. And let me tell you, things are about to get really interesting.
Interesting, and you could say a little unpredictable.
Unpredictable. Okay, you've got my attention.
We're looking at a paper all about those tricky error terms that pop up in mathematics, you know?
Error terms, right. For those of us who, haven't exactly been brushing up on our advanced calculus lately, what are we talking about when we say error terms?
Imagine baking a cake, yeah. You follow that recipe perfectly, but sometimes that cake rises a bit higher. Or maybe it's a little flatter than you expected. Those little deviations, those variations, they're kind of like error terms in math.
Interesting. So it's like the difference between the mathematical recipe and the actual cake we end up with.
Exactly. And, this paper, it's tackling something called the Dirichlet Divisor Problem. It's all about trying to figure out how far off our predictions can be when we're trying to, estimate the number of divisors a number has.
Divisors, right. So just as a refresher, those are the numbers that divide evenly into another number.
You got it.
Like if we take 12, the divisors would be 1, 2, 3, 4, 6, and 12 itself.
Precisely. And, we have formulas for this kind of thing, for estimating those divisors. But it's like your cake, not always perfect. Sometimes there's a difference between how many divisors we think there should be and how many there actually are.
And that difference, that's our error term.
Exactly.
So this Dirichlet, he was trying to measure how big those errors can actually get.
Well, Dirichlet, he was really a pioneer in this whole area of math. You see, he really laid the foundation for understanding these error terms.
Okay.
And to describe, how large those errors could be, how far off they can get, mathematicians use something called Big O notation.
Big O notation. That sounds a little intimidating, if I'm being honest.
I promise. It's not as scary as it sounds. Think of it like setting a speed limit, like how off our divisor prediction can be.
Okay, I think I'm following you.
Big O notation just helps us get a handle on, the potential size of those errors.
Okay, that makes sense. So we've got these error terms, sometimes big, sometimes small, sometimes predictable, sometimes maybe not so much. So where are we at now? Have we figured out these divisor discrepancies?
Well, that's the really interesting part. Even with all the tools, all the brilliant mathematicians working on it, this Dirichlet divisor problem, it's still partially unsolved.
Really?
Yeah, and the paper we're looking at today, it dives into some really cutting-edge attempts to try and unravel this whole thing.
Okay, now you've got to tell me, who are these mathematical daredevils trying to wrangle these error terms? So we've got this unsolved mystery on our hands, this mathematical recipe where the results don't always quite match up. So who are the master chefs, the math whizzes, trying to make sense of it all?
Well, one name you hear a lot in this area is G.H. Hardy, kind of a legend in the world of mathematics.
Hardy. Okay, that name rings a bell. Didn't he write that book, A Mathematician's Apology? The one where he talks about, the beauty of pure mathematics?
That's the one. And his work on this Dirichlet divisor problem, it really is like that. Really elegant, really groundbreaking stuff.
Okay, so what did he do?
So Hardy, he developed something called an omega result.
Omega result. Catchy.
Yeah, it sounds a little complicated, but basically it tells us just how much those error terms can, go wild. How far they can stray from what we expect.
Okay, so it's like a warning label on our mathematical recipe, like caution. Results may vary.
Yeah, you could think of it like that. But the thing is, how do you even start to measure something as unpredictable as these errors?
Good question.
Well, that's where Hardy's work gets really clever. His omega result, and I'll spare you the really technical details here, it essentially sets a kind of a lower limit for how large those errors can get.
Okay.
It's not the complete picture, but it's a really important piece of the puzzle.
So Hardy gives us this kind of baseline, this way of understanding how big these errors can potentially get. Who takes the baton from there?
Well, that's where Kannan Soundarajing comes in. Well, you could say he's a bit of a math whiz himself.
Okay.
And he took Hardy's work and really sharpened it.
Okay, how so?
So he refined those omega results.
Yeah.
And that gives us an even clearer picture of just how big these error terms can actually get.
Okay, so we're starting to get a better handle on the potential size of these errors. But this paper we're diving into, it doesn't just stop there, does it?
You're right, it doesn't. And that's what's really exciting about this. Because they're not just looking at the biggest possible error, the maximum size. They're trying to understand the whole distribution of that error term.
Distribution. Now, it sounds like we're getting into probability and statistics here.
Exactly. Yeah, and that's what's so cool about this research. It brings together these different areas of math that you wouldn't necessarily think go together.
Okay.
It's like, imagine you're combining ingredients for a recipe, right? But instead of exact measurements, you're adding a totally random amount of each ingredient.
Okay. Now, that sounds like a recipe for disaster.
It might sound chaotic, but even with that randomness, there's still going to be patterns in how those ingredients interact, right?
Yeah, I guess so.
Some combinations are going to be more likely than others. And this paper, it argues that the error term in this divisor problem, it behaves in a similar way.
Interesting.
We can't predict any single error exactly, but we can start to understand the overall chances of certain errors happening.
So instead of just looking at the biggest, most extreme errors, these mathematicians are saying, hey, let's look at all the possible errors and how often they pop up.
Exactly. And to do this, they use this, well, it's kind of cool tool, actually. It's called a random trigonometric series.
How, a random what now? You're going to have to break that one down for me.
Okay, so imagine, instead of flour and sugar, our recipe now uses waves.
Waves, like ocean waves.
Yeah, exactly. Each wave, it has its own size, its own speed, right?
Right.
Now, imagine taking a bunch of those waves and randomly choosing those properties.
Yeah.
That's kind of a simplified way to think about these random trigonometric series.
Okay, so I'm trying to picture this wave recipe, but why use something so, well, random to model a number theory problem?
Because it turns out that these random waves, they can actually capture that unpredictable nature of the error term in this divisor problem.
Interesting.
This paper, it makes this really cool connection between these random series and this classic number theory problem. It's a whole new way of looking at it.
So they're saying there's this hidden structure within the randomness of these errors.
Yeah.
Something that we can start to understand using these random waves of all things.
You got it. And that leads us to one of the big findings of this paper, Theorem 1.3.
Okay.
And it's through this theorem that they start to really quantify how often those unexpected errors actually occur.
So Theorem 1.3, that's like the aha moment, the breakthrough in figuring out how often those recipe experiments go, well, maybe not exactly according to plan.
You could say that. It's a big deal because it gives us a way to connect the way the error term behaves to this solid probabilistic model. And that's big because for a long time, people didn't think that kind of connection was even possible.
So we've got Theorem 1.3, this big breakthrough in predicting those mathematical curveballs, those errors. Does that mean we've got it all figured out? Have we finally tamed these wild error terms?
It's a huge step, definitely. But, it wouldn't be a good mystery if there weren't more layers to uncover.
Okay, so what are we missing? What else is there?
Well, Theorem 1.3, it gives us this amazing insight, but it does have its limits.
Limits. You're saying even with these random waves and all these probability models, there's still some things we just can't know.
Think back to our recipe analogy. So, Theorem 1.3, it helps us figure out how likely certain outcomes are, but only within a certain range of randomness,
Oh.
But what if we just start throwing ingredients in there with no rhyme or reason, way outside our normal measurements?
Okay, now you're talking about a whole gallon of milk when the recipe calls for a teaspoon.
Exactly. After a certain point, the model, as good as it is, it starts to break down. We can't really predict those really extreme cases, those outliers. They're just beyond what we can understand right now.
So there's still a mystery here, a whole frontier we haven't explored yet in understanding these errors.
Absolutely.
Yeah.
And that's where Soundarajan's conjecture comes in. Remember we talked about that earlier.
Yeah, he was the one who thinks we're close to understanding the maximum size of those errors, right?
Exactly. He believes that even with these limitations, we're actually really close to pinning down that true maximum size of the error term.
So he's saying there's a limit, even though we hasn't quite found it yet. There's a ceiling on how wild these errors can actually get.
That's right. Imagine if we could actually nail down that perfect recipe, if we could predict those really wild outliers.
That would be huge, a real mathematical triumph. But hey, before we get too carried away with the food metaphors here, we've got to address the elephant in the room. Or maybe we should call it a circle. And a zeta function, too, because this paper, it doesn't just deal with the Dirichlet Divisor Problem, does it?
You're right, it doesn't stop there. And that's what makes it even more interesting. Because this whole thing with error terms, these questions about predictability in systems that seem totally random, they pop up in other areas of math, too.
Oh, really? Like where?
We'll take the Gauss Circle Problem, for example. It's all about trying to estimate how many points you can fit inside a circle.
Okay, so now we're dealing with shapes, different kind of geometry puzzle, but still with those same challenges with the error terms.
Exactly. And it even goes beyond that to things like the Riemann Zeta Function. That's a really fascinating area of number theory.
So from divisors to circles to zeta functions, sounds like this paper is uncovering some kind of like secret mathematical web connecting all these different ideas.
It's the beauty of math. It's full of these surprising connections. This paper, it just gives us a peek at how interconnected everything really is. And, the most exciting part is that we're just getting started. We've only scratched the surface.
So where do we go from here? What's the next chapter in the story?
That is the million-dollar question. This paper gives us these amazing new tools for understanding error terms, but there's still so much we don't know. Can we push those boundaries even further? Can we make our models even better so we can finally predict those really crazy outliers?
Yeah.
And can we really map out this web of mathematical connections, see how deep it goes?
Sounds like the adventure's just beginning. So to everyone listening, next time you're baking a cake, maybe trying to guess how many jelly beans are in a jar, remember this. Even in those things that seem totally random, there might just be a hidden structure, a pattern waiting to be found. And who knows? Maybe you'll be the one to crack the code. All right, so today we're diving into some seriously cool number theory. We're talking error terms and not just the easy ones.
Yeah.
We're talking like Dirichlet Divisor Problem, Gauss's Circle Problem, the classic.
The real deal.
And Youness Lamzouri's paper on the distribution of the error terms gives us the perfect roadmap.
Well, and it's so fascinating, right? Because, you think about this area and it connects things that you might not expect, right? We're talking very structured mathematical problems. But to understand them really deeply, we need to start talking about randomness.
Randomness. Okay, now that's a curveball I would not have seen coming. Before we get lost in the weeds, though, let's make sure everyone listening is on the same page. So we're talking about how many ways you can divide a number, the Dirichlet problem.
Okay.
Or how many dots can fit in a circle, the Gauss problem, right?
Exactly. Both problems. They involve trying to make these approximations. And we can get close to the answer, but there's always this little gap, an error. And that error, it's not just some random thing. It has these fascinating patterns. And it behaves in ways that we're still trying to fully grasp.
So Lamzouri's paper, that's our deep dive into those patterns, trying to decode the secret language of these error terms. What's the big treasure we're hoping to find?
I think the treasure map here is understanding the core of what Lamzouri's doing and why it's important and why it's causing such a stir in the math world. Because it's really pushing the boundaries of what we know about these very classic problems. And maybe, just maybe, getting us closer to solving some of these really long-standing mysteries.
Okay, you've got me intrigued. So, Lamzouri spends a good chunk of this paper on the Dirichlet Divisor Problem, specifically this thing called this delta dot x. Now, I love a good mathematical puzzle, and this delta x, it sounds like a real head-scratcher.
Oh, it's a tricky one. It really is. Imagine trying to pin down a constantly shifting shadow. It's always there, but its shape and its size are always just a little bit off. Mathematicians have been really trying to get a grip on what is the smallest possible value for a certain constant called alpha in this problem. And Dirichlet himself took the first crack at it, and then Voronoi refined his approach, and Huxley brought us even closer. So it's like this relay race of brilliant minds.
Oh, and just when you think it couldn't get any more intriguing, Lamzouri throws in this probabilistic random model. Now, how does randomness fit into this very precise, very deterministic world of number theory? That's what I find so fascinating.
Well, it seems counterintuitive, right? But imagine, if you will, trying to understand how leaves fall from a tree. You could try to track each leaf individually. Or you could use probability to describe the general pattern of their descent.
So we're stepping back, we're looking at the bigger picture. using probability to find patterns in what seems like chaos.
Precisely. So instead of focusing on each individual error, we're looking at the overall distribution of these errors using this thing called, it's a random trigonometric series. It's denoted by fx. And what's surprising is that this random series, it actually has a deep connection to our error term, our delta x.
Okay, now we're talking. But how do we even begin to connect something as neat and tidy as divisors with something as unpredictable as a random series of trig functions?
Well, the bridge connecting these two seemingly different worlds is this thing called the Voronoi summation formula. I won't bore you with the really nitty-gritty details, but it essentially acts like a mathematical translator, allowing us to express our error term, our delta x, in the language of this random model, our fx.
So it's like we're using a secret decoder ring to decipher the language of error terms. And I'm guessing this is where Theorem 1.2 comes into play. It mentions this match between the real error term and this random model. So what exactly is being matched here, and why is that so important?
Yeah, you're spot on. So Theorem 1.2 introduces this concept called discrepancy, which measures how well our random model reflects the actual error term. Think of it like comparing a weather simulation to the real weather. The smaller the difference, the better the model.
So a small discrepancy means our weather simulation is doing a good job of predicting the real-world behavior
of these error terms, right? And a better model means that we can understand these errors more deeply. But what makes this particular theorem so groundbreaking?
It's not just about understanding it better. What's really cool is that improving the accuracy of our model, tightening the bound on that discrepancy, relies on solving a problem in a completely different area of math, computational geometry. It's like finding this hidden tunnel between two seemingly separate caves. Whoa, hold on. We're talking divisors, randomness, and now geometry. This is what I love about these deep dives. You never know where they're going to go. But how does geometry even enter the picture here?
Well, it's connected to this thing called the square root problem in computational geometry, which deals with the efficiency of algorithms used to determine shapes and patterns in large data sets. And as it turns out, the tools and techniques used to tackle that problem have a direct impact on how well we can bound the discrepancy in Theorem 1.2.
So it's like mathematicians have stumbled upon this unexpected link, this hidden passageway between these different mathematical worlds. That's incredible. Okay, but let's shift gears a bit. Lamzouri doesn't just stop at the probabilistic connection. He also delves into those moments when the error term goes a bit wild. Those large values that really throw a wrench in our neat approximations. What makes those large values so interesting?
Imagine you're trying to predict the stock market, right? Most of the time, you might be able to identify trends, make educated guesses. But then there are those outlier days, those sudden spikes or dips that nobody sees coming. Those large values in the error term, they're kind of like that. They represent those unpredictable swings away from the expected behavior.
So we're talking about those moments when the error term goes rogue. And understanding how often and how dramatically this happens gives us a deeper insight into the overall behavior of these errors.
Exactly. And thankfully, we're not starting from scratch. Heath Brown gave us some initial bounds on these large values, but things got even more interesting with the work of Bleher, Cheng, Dyson, Leibowitz. Quite the team, and especially Lau and Montgomery. They really pushed the boundaries of what we know about these outliers.
And their work culminates in those intriguing bounds laid out in equation 1.5. I'm guessing these aren't your run-of-the-mill equations. What kind of secrets do they hold about these unruly error terms?
These bounds give us a much clearer picture of how often those large and small values occur. It's like having a map that shows us the probability of encountering those rogue waves in a vast ocean of numbers.
Okay, I'm starting to see why those bounds are so important, but we're talking about incredibly complex calculations here. What's the takeaway message for those of us who aren't fluent in the language of advanced mathematics? What does this all mean in the grand scheme of things?
It means that even with all of our sophisticated mathematical tools, these error terms still have an element of unpredictability to them, a certain mystique. It makes you appreciate the ingenuity of mathematicians, who can even come close to pinning down these values, let alone develop bounds that describe their behavior.
It's like trying to catch lightning in a bottle. But speaking of breakthroughs, Theorem 1.3 really caught my eye. What makes it stand out from the earlier results? Based on that probabilistic model, it seems like a significant leap forward. In our understanding of these error terms,
it is a significant leap. Remember how we were using that random model, fx, to understand the real error term, delta x? Well, Theorem 1.3 takes this bold step and gives us bounds directly related to delta x itself, without relying on that probabilistic middleman.
So it's like we finally managed to get a direct line to the source, cutting through the noise and complexity of the random model.
You could say that. It's a testament to the power of Lamzouri's techniques, that he could achieve this direct connection. Of course, even this theorem has its limitations.
Limitations. Now you've got me really curious. What kind of limitations are we talking about? Are these like mathematical roadblocks preventing us from fully unlocking the secrets of these error terms?
It's more like we've reached a plateau on our climb. Theorem 1.3 gives us incredibly powerful bounds, but they only hold true within a certain range of values. Imagine looking through a telescope. You can see incredibly far, but there's still a limit to how much of the universe you can observe.
So what happens when we reach the edge of that telescope's view? What's preventing us from seeing further, from pushing those bounds even further?
That's the million-dollar question, and it's tied to some of the biggest unsolved problems in this area of math. For the Dirichlet Divisor Problem, that roadblock is conjecture 1.1. If we could somehow break through that barrier, it would be a monumental achievement.
It sounds like we're talking about a mathematical Everest here. But before we get too caught up in the challenges of the Dirichlet problem, we can't forget about its equally fascinating cousin, the Gauss Circle Problem. Does Lamzouri's paper give us the same kind of insights into those circular error terms?
It absolutely does. And what's remarkable is that many of the techniques Lamzouri developed for the divisor problem translate surprisingly well to the circle problem. It's like discovering that the same key can unlock two seemingly different doors.
So we're seeing these intriguing parallels, these echoes of similar patterns. Across these classic problems, it makes you wonder if there's some deeper underlying structure connecting them all.
That's precisely what makes this area of research so captivating. For example, theorems 1.5 and 1.6 in the paper give us analogous results for the circle problem, showing that those error terms dance to a similar, albeit slightly different, tune.
Slightly different, you say. What kind of nuances make the circle problem stand out from its divisor counterpart?
One key difference pops up in equation 2.6, where we encounter a different exponent. Compared to the analogous equation for the divisor problem, it's a subtle shift. But in the world of mathematics, even small changes can have profound implications.
It's like these problems are speaking different dialects of the same mathematical language. And speaking of different languages, Lamzouri doesn't just stop at the divisor and circle problems. He even ventures into the realm of the Riemann Zeta Function, arguably the most famous unsolved problem in all of mathematics. What kind of connections does he uncover there?
He finds that the tools and insights we've been discussing extend even to the Riemann Zeta Function. It's a testament to the interconnectedness of mathematics, how seemingly disparate areas can share such deep and meaningful relationships.
It's like finding a hidden passageway connecting different continents. It makes you wonder what other mathematical treasures are waiting to be unearthed. But let's take a step back and appreciate just how far we've come on this deep dive. We started with these seemingly simple questions about divisors and dots in a circle, and we've ended up on a journey through randomness, geometry, and even the enigmatic Riemann Zeta Function.
It's been quite the adventure, and what's truly exciting is that we've only just scratched the surface. Lamzouri's work opens up this whole new avenue of exploration, pushing the boundaries of what we thought we knew about these classic problems.
So where do we go from here? What new mysteries are mathematicians grappling with in this world of error terms?
The quest to conquer those unsolved conjectures continues. For the circle problem, it's all about tackling conjecture 1.7. A challenge worthy of any aspiring mathematical mountaineer. And when it comes to the Riemann Zeta function, well, that's a whole other deep dive waiting to happen.
Well, I think we've given our listeners plenty to ponder for now. This deep dive has been a whirlwind tour through some of the most fascinating and challenging problems in number theory. Who knew that something as seemingly insignificant as an error term could lead us down such a profound and rewarding path of discovery?
It's a testament to the power of curiosity and the relentless pursuit of knowledge that drives mathematicians to unravel the secrets hidden within these mathematical puzzles. Who knows what breakthroughs await us just around the corner?
And who knows, maybe one of our listeners will be the one to make those breakthroughs. After all, every great mathematical journey begins with a single step, a spark of curiosity, and a willingness to dive deep into the unknown.
It's more like we've reached a plateau on our climb. Theorem 1.3 gives us these incredibly powerful bounds, but they only hold true within a certain range of values. Mentions like looking through a telescope, you can see incredibly far, but there's still a limit to how much of the universe you can observe.
So what happens when we reach the edge of that telescope's view? What's preventing us from seeing further, from pushing those bounds even further?
Well, that's the million-dollar question, right? And it's tied to some of the biggest unsolved problems in, this whole area of math. For the Dirichlet Divisor Problem, that roadblock is conjecture 1.1. If we could somehow, break through that barrier, it would be it'd be a monumental achievement.
It sounds like we're talking about a mathematical Everest here. But before we get too caught up in the challenges of the Dirichlet problem, we can't forget about its equally fascinating cousin, the Gauss Circle Problem. Does Lamzouri's paper give us the same kind of insights into those circular error terms?
It absolutely does. And what's remarkable is that many of the techniques Lamzouri developed for the divisor problem, they translate surprisingly well to the circle problem. It's like discovering that the same key can unlock two seemingly different doors.
So we're seeing these intriguing parallels, these echoes of similar patterns across these classic problems. It makes you wonder if there's some deeper underlying structure connecting them all.
That's precisely what makes this area of research so captivating. For example, theorems 1.5 and 1.6 of the paper give us analogous results for the circle problem, showing that those error terms, they dance to a similar, albeit slightly different tune.
Slightly different, you say. What kind of nuances make the circle problem stand out from its divisor counterpart?
Well, one key difference pops up in equation 2.6, where we encounter a different exponent compared to the analogous equation for the divisor problem. It's a subtle shift, but in the world of mathematics, even small changes can have profound implications.
It's like these problems are speaking different dialects of the same mathematical language. And speaking of different languages, Lamzouri doesn't just stop at the divisor and circle problems. He even ventures into the realm of the Riemann Zeta Function, arguably the most famous unsolved problem in all of mathematics. What kind of connections does he uncover there?
He finds that the tools and insights we've been discussing, they extend even to the Riemann Zeta Function. It's a testament to the interconnectedness of mathematics, how seemingly disparate areas can share such deep and meaningful relationships.
It's like finding a hidden passageway connecting different continents. It makes you wonder what other mathematical treasures are waiting to be unearthed. But let's take a step back and appreciate just how far we've come on this deep dive. We started with these seemingly simple questions about divisors and dots in a circle, and we've ended up on a journey through randomness, geometry, and even the enigmatic Riemann Zeta Function.
It's been quite the adventure, and what's truly exciting is that we've only just scratched the surface. Lamzouri's work, it opens up this whole new avenue of exploration, pushing the boundaries of what we thought we knew about these classic problems.
So where do we go from here? What new mysteries are mathematicians grappling with in this world of error terms?
Well, the quest to conquer those unsolved conjectures continues. For the circle problem, it's all about tackling conjecture 1.7, a challenge worthy of any aspiring mathematical mountaineer. And when it comes to the Riemann Zeta Function, well, that's a whole other deep dive waiting to happen.
Well, I think we've given our listeners plenty to ponder for now. This deep dive has been a whirlwind tour through some of the most fascinating and challenging problems in number theory. Who knew that something as seemingly insignificant as an error term could lead us down such a profound and rewarding path of discovery?
It's a testament to the power of curiosity and the relentless pursuit of knowledge that drives mathematicians to unravel the secrets hidden within these mathematical puzzles. Who knows what breakthroughs await us just around the corner?
And who knows, maybe one of our listeners will be the one to make those breakthroughs. After all, every great mathematical journey, it begins with a single step, a spark of curiosity, and a willingness to dive deep into the unknown.
Ever find yourself looking for patterns in weird places?
Oh, yeah.
I don't know, the way the leaves fall off the trees or the way traffic backs up at certain times of day.
Sure.
Well, today, get ready because we're about to dive into a world where even numbers, the things we think are the most predictable, can be totally unpredictable.
It's true. Sometimes, the most elegant math problems are the ones that just leave us totally stumped.
We're talking about a paper, a recent one, by Youness Lamzouri.
Okay.
It's all about something called the Dirichlet Divisor Problem. It might sound kind of intimidating, but Stick with us.
Yeah.
The idea at the heart of it is actually pretty simple.
All right.
So divisors. Let's start there.
Yeah. Okay, think of any number. How about 12?
Okay, 12.
The divisors of 12 are all the numbers that divide into it perfectly. No leftovers. 1, 2, 3, 4, 6, and 12 itself.
Got it.
So that divisor function, mathematicians write it DAN, it just tells you how many divisors a number has. For 12, D12 would be 6.
6, because there are 6 divisors.
Yeah.
Makes sense.
Right. Now, this Dirichlet Divisor Problem, it kicks things up a notch. It asks, can we find like a truly reliable formula to predict the total number of divisors, but like for all numbers up to a certain point?
Okay, so like if we want to add up all the divisors for the numbers from 1 all the way to, say, 100.
Exactly. That's where this problem really gets cooking. Mathematicians, they want a precise answer, not just, it's got to be somewhere around this number.
Right.
And here's the thing. We actually do have a formula that works. But it's not perfect. It always has a little bit of like a mathematical fudge factor.
Like when I try to bake a cake and I'm always off by a teaspoon of flour or something like that.
That's actually a really good analogy. Because it's close, it's just not perfect. And that error, that teaspoon of flour, that's what Lamzouri's really digging into.
Mm-hmm.
We call that error.
It sounds almost like mysterious.
Right.
But, I mean, why should we care about this tiny little error? Is it really that important?
It might seem insignificant, just a small blip on the radar.
Right.
But CX actually gives us a glimpse into something way more fundamental about numbers. Think of it like this. CX behaves kind of like someone who's had a few too many drinks and they're stumbling around randomly.
Okay.
Each step they take is unpredictable on its own, but if you watch them long enough, you start to see these patterns emerge.
So are we like venturing into the world of probability now? I didn't realize numbers could be so unpredictable.
And that's the thing, it's all connected. This drunkard's walk, that's actually a real term in probability theory.
Oh.
And it turns out this same kind of randomness, it pops up in how these divisors are distributed. So understanding, it's not about making our formula perfect, it's about understanding the inherent messiness in a system that we think of as perfectly ordered.
Okay, that's actually really fascinating. So how does Lamzouri even begin to study something so seemingly random?
Well, he uses a super clever approach. He compares the way John Chubb jumps around to something that seems totally unrelated at first.
What's that?
Flipping a coin.
Hold on. Coin flips. Now we're talking.
Yeah.
But how can flipping a coin tell us anything about, these mathematical errors?
It might seem strange, but mathematicians use these things called probabilistic models to study these kinds of problems.
Okay.
Lamzouri, he realized the way Lex behaves, it's actually comparable to the randomness we see in coin tosses. It's like one of those aha moments in math where you connect two completely different things.
I'm hooked. So he's comparing this error term to flipping a coin. What's he hoping to find?
He's looking for something called discrepancy. Imagine you have a perfectly fair coin. You flip it 100 times.
Yeah.
You'd expect statistically to get something close to 50 heads, 50 tails, right?
Yeah.
Discrepancy measures how far off the actual results are from what statistics tells us should happen.
So he's looking at how much the actual error that differs from what we'd expect if it truly were as random as flipping a coin.
Exactly. And what Lamzouri finds is really intriguing. The discrepancy, it exists, but it's surprisingly small. So it's behaving much more predictably than pure randomness would suggest.
So even though there's randomness built in, there are still some hidden rules governing these errors.
Exactly. And that is huge E. It suggests there's a deeper structure to Lex than we initially thought, something subtly but significantly influencing how it behaves.
This is where it gets really, really interesting.
Yeah.
So we call it an error, but are you saying this AHIC, it might actually have a predictable pattern?
It's not quite that simple. Not like saying, oh, here's the equation. It'll perfectly predict it all.
Okay.
But this small discrepancy, it really hints that there's a hidden order within the chaos. That's what makes Lamzouri's work so fascinating. It opens up a totally new way of looking at these mysteries in number theory.
It's like we've been listening to static on a radio thinking it's just noise. And now we're like, wait, is that a voice? Is there a message hidden in there?
Right. And here's where it gets even wilder. Remember how we were talking about RX being kind of like a drunkard wandering around?
Yeah.
Well, that same kind of behavior, it pops up in a totally different area of math. It's called the Gauss Circle Problem.
Okay. Circles, dots inside the circles, right? I think I vaguely remember this from somewhere.
Exactly. Picture like a circle, but it's drawn on graph paper, with all those little squares.
Yeah.
The Gauss Circle Problem asks, how many of those graph paper dots actually fit inside that circle.
Okay, and I'm guessing, just like our divisor problem, there's a formula, but...
But there's always a little bit of error. That pesky discrepancy again.
No way. So this error term, it's also doing the random walk thing, like our drunkard friend.
Bingo. This error term in the circle problem, it's like a long-lost twin to X from the Dirichlet Divisor Problem. They both have that same, like, intriguing mix of randomness, but with, like, a hint of structure underneath.
Hold on. Are you saying there's a connection between how many numbers divide into another number and how many dots fit in the circle?
You're getting it. That's what's so cool about number theory.
Yeah.
Things that seem totally unrelated on the surface can actually be deeply connected. And Lamzouri's work, it's like he's found a thread that ties these two problems together. He even found those discrepancy results, those small errors. They're similar in the circle problem, too.
Man, this is blowing my mind. We started with dividing numbers, and now we're talking about probability, prime numbers, dots and circles. It's like every time we answer a question in math, it's like 10 more pop up.
That's the fun of it, right? But it's not just about the math itself. It's about what this tells us about, like, the nature of prediction itself.
Okay, now you really have my attention. Math and predicting the future.
Think about it. If even numbers, right, the things we think are the most predictable things in the universe, if even they have this baked-in randomness, this messiness, what does that say about our ability to predict anything with perfect accuracy?
Whoa. That is actually kind of a scary thought, like the universe just has a built-in margin of error or something like that.
Exactly. And understanding that margin of error, that's huge EE, not just in math, but in anything that involves predictions, statistics, financial markets, even weather forecasting, you name it. This unpredictability, it's always there, lurking beneath the surface.
So it really makes you think twice about all those predictions we rely on, you know?
Yeah.
Like, maybe we can't know everything with absolute certainty.
Right. It's humbling, in a way. But it's also kind of exciting.
How so?
Because those limitations, they don't mean we should just give up trying to understand things.
Right.
If anything, it makes the whole pursuit of knowledge that much more interesting, you know?
Yeah, like, because the answers might not be as clear-cut as we thought they were.
Exactly. It's in those gray areas, those margins of error, that's where the really groundbreaking stuff happens.
You mentioned earlier that Lamzouri, he had to make a few assumptions in his research, right? Something to do with square roots.
Oh, yeah, that's an important point to really connect all the dots here between the divisor problem, that circle problem we talked about, and potentially even something as huge GE as the Riemann hypothesis.
Okay, yeah.
Lamzouri, he had to make some assumptions about how independent square roots are.
Independent, like two coin flips. One result doesn't affect the other.
Exactly. He's assuming the distribution of square roots, it behaves in a specific way, and that's what lets him draw all these fascinating connections.
Okay, so there's a chance those assumptions, they might not be totally spot on.
It's possible, and that's where it gets really interesting. If those assumptions need even a little tweaking, it could have huge GE ripple effects.
Like, we've been building this amazing mathematical tower, and now we're wondering if the foundation's secure.
That's a great way to put it. But, you know, that's science for you, right? Answer one question, 10 more pop up. And sometimes those new questions, they make us go back and re-examine everything we thought we knew.
So where does that leave us? Back to square one?
Not at all. Even if Lamzouri's assumptions need a little revising, the connections he's made, they're still hugely important. They give us this glimpse into something deeper going on in number theory, like a hidden structure we're just starting to see the outlines of.
So this error term, this bit of messiness in the numbers, it might be the key to unlocking even bigger mathematical secrets.
That's the idea. It's like a constant reminder that the universe is full of surprises, the most unexpected discoveries. They often come from embracing the unknown, from digging into those little inconsistencies that make you go, that's weird.
And that is our deep dive for today. From dividing numbers, we ended up in a world of probability, randomness, and the limits of what we can actually predict. It's incredible how something as seemingly insignificant as a little bit of error can lead to such mind-blowing possibilities.
Couldn't have said it better myself. It really shows the power of curiosity, right?
Absolutely. Never stop asking questions, everyone, because who knows what you might discover hiding in the margins of those answers. Okay, so imagine you're trying to, like, count all the sprinkles on one of those giant cakes, one's totally covered.
Oh, I see, like those sprinkle-covered cakes.
Yeah, exactly. It sounds fun, but it would be kind of impossible, right? You've got sprinkles all clustered together, then some right on the edge. Like, is it on the cake or not?
Yeah, I can see how that would be surprisingly tricky.
Right. It's not as easy as it sounds. Well, that's kind of the challenge that mathematicians love to sink their teeth into. And today we're going deep into the world of number theory, where these sprinkle problems, as I'm calling them, get seriously fascinating.
I'm all ears. Let's talk sprinkles.
So we're looking at research you send over on two specific problems, the Dirichlet Divisor Problem, and this one's a mouthful, the Gauss Circle Problem.
And what's really cool about these problems is how what seem like pretty simple questions like how many ways can you divide a number or how many points can you fit inside a circle, these actually lead to some seriously deep, even profound mathematical concepts.
It's like those sprinkles are hiding some deeper truth about the universe of numbers.
Exactly. We're talking about the very essence of numbers and whether they're ultimately predictable or not, which, spoiler alert, they're not always.
All right, you've piqued my curiosity. Let's unpack these problems. Let's start with the Dirichlet Divisor Problem. From what I understand, it's about figuring out how many divisors a number has. Sounds straightforward enough, but I'm guessing there's a twist.
Oh, there's always a twist in number theory. So yeah, with small numbers, it's easy peasy. Take the number 12, for instance. It has 6 divisors. 1, 2, 3, 4, 6, and 12. No problem there. But when you start dealing with astronomically huge numbers, well, you need formulas to even come close to predicting those divisors.
Because counting them one by one just isn't feasible.
Exactly. And even with formulas, there's always a little bit of a margin for error, a kind of mathematical fudge factor. We call that the error term. And it's usually represented by the symbol delta x. That's a Greek letter delta, by the way, just in case anyone's following along at home.
So delta x is like the difference between what our fancy formula predicts and the actual number of divisors.
You got it. Think of it like this. Dirichlet, total genius, came up with this clever method for estimating divisors using this shape called a hyperbola. Imagine you have this giant sprinkle-covered cake again, right?
I'm with you.
Okay, now picture trying to, neatly cut this cake using a hyperbola-shaped knife. That's kind of what Dirichlet did with his method. It was a huge leap forward, but it still left some crumbs behind, and those crumbs, my friend, that's our delta x.
And I'm betting mathematicians don't just sweep those crumbs under the rug.
Yeah.
They're important, right?
Oh, you better believe it. Those crumbs, as insignificant as they might seem, hold a lot of weight in the math world. Later on, other brilliant minds like Voronoi and Huxley, they came up with even more ingenious ways to slice that cake, metaphorically speaking, to try and make those crumbs, that delta x, smaller and smaller, but get rid of them entirely.
That's the million-dollar question.
Yeah, that's the holy grail. Still an unsolved mystery, I'm afraid.
So even though we've gotten way better at predicting these divisors, there's always this teensy bit of unpredictability. Like, numbers just refuse to be completely tamed.
That's the beauty of it. And to make things even more interesting, we have these things called, get ready for it, omega results. They're basically like setting a lower limit on how bad those crumbs, that delta x, can get.
Hold on. So it's not just that we haven't cracked the code yet. We actually know definitively that there are situations where the error, those pesky crumbs, are going to be surprisingly large.
You nailed it. It's like we zoomed in on our sprinkle cake and found these zones that are way more densely packed than others. And no matter what we do, our predictions always seem to underestimate those clusters. And that leads us to a fascinating question. Is there some kind of deeper pattern hidden within this randomness, within the crumbs themselves?
This is where it gets juicy, right? Because to dive into that question, mathematicians turn to this powerful tool, probability.
You know, you're spot on with that. Things get really interesting when we bring in probability. It's like we're trying to figure out if some mischievous baker is arranging those sprinkles in a secret pattern, or if it's all just gloriously random.
All right, you've got to tell me more about this. How does probability, which feels kind of random itself, help us understand something as, well, seemingly precise as number theory?
So picture this. Instead of getting bogged down trying to predict the exact location of every single sprinkle on that massive cake, we take a step back.
Okay, I'm following.
We create these things called probabilistic models. These models help us understand the overall behavior of those errors, those pesky crumbs, in a more general sense. One such model, mentioned in the research you sent, is called FX.
FX sounds kind of cool, like a secret agent in the math world.
Ah, I like that. Secret agent FX on a mission to uncover the mysteries of number theory. But in all seriousness, what's really wild is how closely this FX model, which is rooted in probability, actually mirrors the real-world error term we see in the Dirichlet Divisor Problem. It's as if we discovered that, yeah, there are these hidden zones on our sprinkle cake where those clusters are more likely to pop up, even if we can't pinpoint the exact coordinates of each cluster.
So it's not just pure chaos. There's a method to the madness, a pattern to those sprinkle clusters. Even if it's super complex and our brains can't quite grasp it fully.
That's it, exactly. And this whole connection to probability, it's like a giant flashing neon sign screaming, hey, there's something bigger going on here. It's telling us that those errors, those seemingly random crumbs, they actually have some underlying structure.
Mind blown.
Right. But, and this is a big but, every model has limitations. Think of it like using a weather app to get a sense of the chances for rain. It's useful overall, but it can't tell you if that one specific raindrop is going to fall on your head. You might still get caught in a downpour.
Meaning, as powerful as this FX model is, it can't perfectly predict every single sprinkle on our hypothetical cake.
You're catching on fast. There's a point where those very specific errors, they just become too unpredictable, even for the magic of probability. But hey, enough about divisors for a moment. You also sent over some intriguing research on another mathematical puzzle, the Gauss Circle Problem. This one's even easier to visualize, I think.
Oh yeah, the dot problem. I love this one. It's so simple, yet so mind-boggling. We're counting dots inside a circle drawn on a grid, and the errors, well, those come from the dots right on the circle's edge. Are they in or are they out? Always a tough call.
Right. Seems like a world away from dividing numbers, doesn't it? But here's the kicker. The way their error terms behave is astonishingly similar. Remember those omega results we talked about with the divisor problem? The ones that set those lower limits on how bad the errors can get? Well, guess what? They pop up in the circle problem, too. It's like these two problems, as different as they seem on the surface, are somehow connected at a deeper mathematical level.
Well, so maybe those dots and divisors aren't so different after all. It's like they're both tapping into some fundamental truth about numbers, just from different angles.
Now you're talking. It's as if we went back to our sprinkle cake and realized that the divisor part and the circle part, which we thought were totally separate, they actually have these surprisingly similar sprinkle patterns. And it gets even wilder. That research you sent, it hints at applying these same error analysis techniques to even grander mathematical ideas, like the granddaddy of them all, the Riemann Zeta Function.
Oh, I heard whispers about the Riemann Zeta Function. It's like the rock star of the math world. But how does it connect to all of this? Fill me in.
Haha. Rockstar is a good way to put it. It's this mathematical celebrity because it seems to pop up everywhere in mathematics and has this uncanny ability to connect seemingly unrelated ideas. It's like it holds the secrets to the universe of numbers, and the more we learn about it, the more connections we uncover.
So you're telling me these tiny errors, these insignificant crumbs from our divisor and circle problems, might actually hold the keys to unlocking one of the biggest mysteries in mathematics.
It sounds crazy, right? But that's exactly what's so exciting about this whole area of research. It's like those crumbs are breadcrumbs leading us down a path to a whole new level of understanding. And who knows what we'll find along the way.
Okay, my mind is officially blown. So we've established that these errors are not only important, but they might even point to something much, much bigger. But where do we go from here? How do mathematicians even begin to tackle these problems? What's the game plan?
Well, one path forward is to keep digging deeper into those omega results we talked about earlier. Remember, they give us those lower bounds on how bad the errors can get, but there's still a gap between what we know those errors can be and the best upper limits we've been able to prove mathematically.
So it's like we're trying to build a stronger fence around those unpredictable sprinkles, trying to narrow down the range where they can roam free.
Precisely. If we can tighten that fence, if we can shrink that gap, we'll have a much better understanding of just how wild those errors can really get. And that, my friend, could unlock some serious insights into the patterns behind the chaos.
Makes sense. So it's all about getting a tighter grip on those errors. What else is on the agenda for mathematicians tackling these problems?
Another promising avenue is to keep refining those probabilistic models, like our buddy FX. The better we understand these models, the more we can learn from them. It's like upgrading our magnifying glass so we can get an even closer look at those sprinkle clusters, hoping to discern even more intricate patterns and connections that we might have missed before.
So it's about constantly tweaking our tools, coming up with new approaches, and never taking our eye off those elusive sprinkle clusters.
You got it. It's a fascinating dance between creativity and precision. You need that creative spark to come up with new models, new strategies for tackling these age-old problems. And then you need that rigorous precision to really dissect the results to make sure our theories hold water.
And speaking of connections and new approaches, we talked earlier about the tantalizing possibility that there might be some deeper links between these sprinkle problems, as I've come to call them, and other branches of mathematics. Can you elaborate on that a bit?
Absolutely. Remember how we were amazed by the similarities between the circle problem and the divisor problem, even though they seem so different on the surface? Well, there's a growing suspicion among mathematicians that these connections run even deeper than we initially thought. And by borrowing tools and techniques from other mathematical disciplines like our friend probability theory, we might just unlock even more secrets hidden within these classic problems.
So it's like different branches of mathematics are coming together, pooling their collective wisdom to crack the code of these age-old questions.
Precisely. It's a beautiful testament to the interconnected nature of mathematics. What may seem like separate, isolated problems, they often turn out to be different facets of the same underlying truth. Just like with our sprinkle cake, what we initially thought were distinct and separate sections, they're actually intricately interwoven.
It's like realizing that the sprinkle pattern on our cake is actually a tiny reflection of a much grander, more intricate design. We're just starting to see the edges of this massive interconnected mathematical tapestry.
What a fantastic way to put it. And that's what makes this entire area of studies so captivating. It's this constant journey of discovery, uncovering hidden connections and deeper truths about the very fabric of numbers.
Wow, I think I need a moment to process all of this. We've covered a lot of ground. But before we wrap up, is there anything else you want our listeners to take away from our deep dive today? What's the big takeaway here?
You know, so often in mathematics, we get caught up in the thrill of finding those elegant, perfect solutions, those airtight proofs that leave no room for doubt. But honestly, I think there's something equally beautiful, maybe even more profound, about those problems that continue to mystify us, those questions that haven't been neatly resolved. Because it's in those unanswered questions and those lingering errors that we often find the greatest opportunities for discovery.
I love that. It's like those errors are invitations beckoning us to explore further, to delve deeper into the mysteries of mathematics. They're not failures, they're opportunities.
Exactly. So next time you're wrestling with a problem, whether it's a mathematical conundrum or just a real-life head-scratcher, don't be discouraged by those imperfections, those lingering questions. Don't shy away from those errors. Embrace them. Because often it's in those unexpected detours, those moments where we stray from the well-trodden path, that we stumble upon the most fascinating and profound truths.
Beautifully said. And on that note, we'll leave you to continue your own explorations of the amazing world of number theory. Thanks for joining us on this deep dive. It's been a blast. It's like we're seeing those errors in a whole new light, not as mistakes, but as like guideposts pointing us toward uncharted territory, right?
You've got it. And that's what makes this whole field so captivating. It's not just about, checking off boxes and finding answers. It's about embracing the journey, the constant exploration of new ideas.
So what you're saying is, even if we don't fully grasp all the technical intricacies of those omega results or the ins and outs of probabilistic models, our curiosity itself has value.
Absolutely. It's that curiosity, that drive to ask why, that pushes us to dig deeper, to look for those hidden connections, those underlying patterns. And who knows, maybe someday one of those why questions will lead to a major breakthrough.
That's inspiring. It reminds me that even in those sometimes dense research papers, there's a real sense of adventure.
There definitely is. It's like being an explorer, charting unknown territory. Every new insight, every unexpected twist and turn, it just adds to the excitement.
So as we wrap up our deep dive today, any final thoughts for our listeners? Something to leave them pondering as they continue their own exploration of these ideas?
How about this? Imagine those error terms we've been discussing as like constellations in the night sky. We've identified some of the stars, some of the patterns, but there are still vast, uncharted regions out there just waiting to be explored.
Ooh, I love that analogy. It really captures that sense of wonder and possibility.
Exactly. We've only just begun to scratch the surface of what these error terms might reveal about the nature of numbers, about the very fabric of mathematics. Who knows what other hidden connections, what other mind-blowing mathematical truths are waiting to be discovered?
It's exciting to think about all the potential breakthroughs that might be just around the corner.
It really is, and the best part is anyone can join this exploration. All it takes is a curious mind and a willingness to embrace the unknown.
Beautifully said. And on that note, we'll leave you to continue your own explorations of the fascinating world of number theory. Thanks for joining us on this deep dive.